Hello again and welcome to the first lesson on Chapter 10, Forces and Motion, from the Year 12 portion of the course. So we're going to be building on what we saw in Chapter 9, where we looked at a constant acceleration and applying that in terms of Newton's three laws of motion. So the chapter starts fairly lightly, but by the end, Chapter 10.5, 10.6, the questions do get more involved. So a good grounding on this is essential. And on that note, let's get started with a warm-up so that you're all in the mood and ready to go. So here are 4 questions, almost as ever, to have a go at. So try these yourselves if you can. Press play when you're ready to see the solutions. Pause the video now and try these on your own first. And like I say, press play when you've done them all as best as you can and you want to see if you got them correct or not. So without further ado, let's have a look now at question number 1. So for question 1, we have a random variable x which is binomially distributed. So x is binomial. We've got 15 trials. The probability of success is 0.2. So for part A, we have to find the probability that we have 3 successes. The probability for x is equal to 3. So I'm going to recap how we do this using a class whiz. Of course, as ever, you can also use a binomial tables given to you at the back of the official formula booklet. So without further ado though, I'm just going to remind you how to do this on the class whiz. So here it is. So we have to get into the right mode first of all. So we press menu and scroll until we can see this bell curve. This bell curve will make more sense in year 13, I promise you. So press 7 for distribution. Now because we want to work out the probability that x is equal to a certain number, we want to go for binomial PD, so we press option 4. Now we press 2 for variable and we type in what we want. So here what we have is x, so we want to have 3 successes, so we press 3 for the number of successes. Next we have n, which is the total number of trials, which is 15, so we press n as being 15. Finally, the probability of success P is 0.2. So we press 0.2, press equals and equals again. And as you can see, we get 0.250 to 3 significant figures. So about a quarter chance, 1 in 4 chance of it being 3. So 0.250. So question B, what the probability that x is up to and including 3. Oops, that's a slight mistake. So we'll say probability that x is up to and including 3, but no more. And so what this means here is we want to consider the probability of x is 0 or 1 or 2 or 3. And so this is cumulative, up to and including 3 successes. So what we want here is to go for the cumulative distribution, binomial PD. So what we do here, we press menu, option 7, but this time we scroll down and click on 1 for binomial CD. And again we can press variable and go for that one. So again this time x in this occasion stands for what we want to go up to and including. We want to go up to and including 3, so this time we leave it as 3, and now press equals again. And as you see, even though we used 3, 15 and 0.2 as before, this probability is greater. It's 0.648, and that's because for the cumulative distribution, we're not just including the probability of it being 3, we're adding to that the probability of x is 2, for x is 1, and x is 0. So there's a big difference between CD and PD. PD works out the chance of it just being a certain singular value. CD is cumulative. It works out the probabilities inclusive of every value up to and including this number here. So that's 0.648. We can now move on and have a look at part C. So for part C, what the probability for x is less than 3. Now, we need to consider it using this symbol always. So if it's less than 3, that's the same as saying what the probability that x is up to 2, but no more than 2. So all we need to do now is to alter the number going up to from 3 to 2. So get the calculator again. Now we can just press AC to go back and alter the parameters. So to press AC, all we need to do now, we're still talking 15 trials, we're still talking that the probability of success is 0.2. The only thing we need to alter here is to change the 3 to a 2. Press equals and equals again, we'll get here 0.398. And so that's our answer to part C. Now for part D, again we need to work in terms of this symbol here when using the cumulative distribution. The probability that x is greater than 3, that's essentially saying it's everything apart from the chance that x is 3 or less. So this one is actually 1 minus the probability that x is 0, 1, 2 or 3. But if you look carefully, we worked this one out earlier in part B. That was 0.648. And so what we need to do here is just simply 1 minus 0.648. So if we try this on the calculator, go to menu, press option 1 to get back to normal mode. I'll move the calculator away so you can see what's happening. So 1 subtract 0.648, that gives us 0.352. And so finally, with a bit of work, of course, we've done now question 1. So that's part D. We'll underline part C as well, so they're all underlined, so it's consistent. So let's have a look at question 2. So question 2, we've got something about probability again. So let's have a read of this question carefully. So if we have a look here, we have two events, A and B, as such that the probability of A is 0.2 and the probability of B is 0.3. And we're told that A and B are statistically independent. We now need to use this information to draw a Venn diagram to represent the information as given. So I'm just going to bring up a general Venn diagram here. So what we'll have is, whoops, not that. So what we need to have is a general sort of rectangular shape like this. Okay, so A and B. And so probability of A is 0.2 and probability of B is 0.3. Now this is often confused. If two events are mutually exclusive, that's when these circles would not overlap. Independent is different. When they're independent, they do overlap. And so because these two events are statistically independent, what this means is, therefore, we can say the probability of A multiplied by the probability of B, that will equal the probability of the event being the intersection of A and B. So that's what it means in a nutshell. So we now know the probability of being A and B combined has to be the same as PA times PB. So in other words, therefore, the probability of being in the intersection of A and B, this overlapping part here, excuse me, that's going to be the probability of A, which is 0.2, multiplied by the probability of B, which is 0.3. So 0.2 multiplied by 0.3, that will give us 0.06. So now it's just a case of filling this in like we need to. So this bit here is going to be 0.06. Not the best colouring in, but you know, I've probably peaked at colouring in when I was about 6 years old. I'm not the best artist, sadly, although I'm not knocking art in any way, shape or form. I'm just saying I'm not particularly very good at it. So that's 0.06. Now we need to fill in the other bits of the Venn diagram as well. So we know that the probability of A is 0.2. This overlap includes a part of A, so this bit here will be 0.2 minus 0.06. And to be honest, now you can think of it in terms of money, unless you want to use your calculator, which is also fine. 0.2 is the same as 0.20. That's like 20p. So 20p minus 6p, that's going to be left with 14p here. Similarly, for probability of B, that's 0.3, which is one of the same as 0.30. So this circle here for B needs to total 30p, but there's already 6p in this overlapping bit. Therefore, the bit left for this bit that does not overlap is 30p minus 6p, which is just 24p. A common thing now, though, is to completely forget and ignore what's on the outside. So remember, for probability, the sum of all probabilities for any one event has to add up to 1. So on the outside, it's going to be 1 subtract all these probabilities here. So we can do this easily enough on the calculator. So we just need to do 1 subtract 0.14, subtract 0.06, subtract 0.24, and we get 14 over 25, which is 0.56 as a decimal. And so that's the Venn diagram completed. So therefore, let's have a look at number 3. Explain the difference between a scalar quantity and a vector quantity. Now, this is crucial, although luckily for everybody who's watching this, it's fairly straightforward to explain. A scalar, essentially, just has a size, whereas a vector has a size and a direction. So to word that a bit more carefully and formally, something like this would do. So a scalar quantity has magnitude, that's a fancy word for size only, magnitude only, whereas a vector has both a vector quantity has both a magnitude and a direction. So a vector has got both of these two components. A scalar's only got one real thing going for it. It's just got a magnitude. Whereas a vector has a magnitude and it acts in a certain direction as well. Let's now have a look at the final one, question 4. We're told here that the velocity of a particle is given by v equals 3i plus 2j. So the I component tells us it's going 3 to the right, and the j component tells us how far up or down it's going. So that means 2 up. So to picture this velocity, it'd be doing something like this. Okay, so I'm not saying this has been drawn to scale, it's just to give you a picture of what's going on. So I'll just make this diagram slightly better. Okay, so 3i means it's 3 in the horizontal direction, whereas 2j means you can think of it as going 2 up. Velocity is a vector quantity. The speed just has size, and so the speed here is just the length of this line. Okay, so speed is just this length here. Velocity is this line size and this direction here. So velocity would be the line size plus the direction, maybe involving theta, whereas speed is just s, which we need to work out. So we can use Pythagoras for this. So the speed is going to be the square root of 2 squared plus 3 squared Okay, so 2 squared plus 3 squared. Now, we could choose to leave this as a exact surd, or we could give it as a rounded fraction, or decimal. So I'm going to leave this as a surd, in fact. So 2 squared plus 3 squared will be root 13. So the speed is root 13 meters per second. Now, whether we use a surd or rounded decimal depends on the context of the question, but the question doesn't say, so I think we're okay to leave it in exact form. The speed is just root 13 meters per second. So now we're suitably warmed up, let's talk about the main bit of today. So, force diagrams. Now, doing a diagram including all forces will underpin your success at mechanics for both year 12 and in particular year 13. So what's going to follow is an introduction to how to do force diagrams, but it's absolutely crucial in terms of scoring heavily and getting maximum marks on the questions. So what is a force diagram? Well, a force diagram is just simply a diagram showing all forces acting on an object, so it's fairly self-explanatory. Each force is shown as an arrow pointing in the direction in which the force acts. Indeed, since forces have both a direction and a magnitude, they are vectors. We can use force diagrams to model problems involving forces. So for each scenario, the idea here is you're going to discuss in pairs, or maybe groups of 3, what forces are acting on the main object. Afterwards, you need to draw a force diagram of the box next to the object under the header first attempt. So I've given you 2 attempts here because this might be new, a mistake might be made with the wording, so hence first attempt is just to get the ideas on paper, second attempt will be the finalised version. So in all cases, to keep things simple, and this is absolutely fine for the examiner, just use a rectangle to represent the object. So first off, we've got scenario, and as I said, first attempt and second attempt. So what's the first one? It's an aeroplane. So this is just me just thinking out loud. So let's imagine our first attempt, we just drew a rectangle. That's a square, I know, before you start questioning. Okay, so that's going to be our plane. And it's going in this direction. So the motion of a plane is going this way. Okay, so what might be making it go forward? Well, we can think of it after, can't we? In terms of pulling it down, there's also going to be a force pulling it down. That's a force we all experience. That's just for weight. So I'm going to call that weight. Going forward, that's the thrust from the engines. But of course, if these were anything acting on the plane, then there'd be nothing from stopping it from falling out of the sky. So we need a force going upwards to counteract, at least in part, the weight. So the force going upwards, acting on the plane, is coming from the underside of the wings, which keep it from falling out of the sky. And a word we can use for that is called the uplift. So that would be a valid first attempt. However, it wouldn't be quite full. There's something we're missing out. So for the second and final attempt, I'd like to see something like this, perhaps. So again, I'll just crush this one to make it into a rectangle. And if you can think or spot already what I'm missing, then that's great. One thing we're missing is a force pulling the plane backwards. Okay, a force resisting the motion. So I'll add the word for that in a moment, but for now, I'm just going to get these all labelled on correctly. So as before, pulling the plane forward is the thrust from the engines. Pulling it down is the weight. That will always feature on any object with weight, so that's essentially, for me and you, any object. Uplift, stopping it from falling out of the sky, but going backwards against the motion is air resistance, which we can call the drag force. Now, as a general convention with force diagrams, to the right is positive, like the x-axis goes to the right. So it would be possible to do this plane travelling to the left, But for standard convention, it's just to think of things going to the right and consider that to be the positive direction. So positive is the thrust, the direction the plane's going. Backwards is the drag force. If the thrust is bigger than the drag, the plane will be accelerating in the positive direction. If it's equal, the plane will be going at a constant horizontal velocity. If the drag is greater than the thrust, the plane will be slowing down, perhaps to land. And it's the same idea with the weight and the uplift. So if the uplift is greater than the weight, for example on takeoff, the plane will be accelerating in the horizontal direction. It'll be going up. If the uplift is less than the weight, the plane will descend. It'll be going down. For example, if it's landing, if they're balanced, the uplift and the weight, the plane will be cruising between its being taking off and landing at its destination. Let's have a look at another one. So a car being pushed. Okay, so what if a car was being pushed? So again, what I'm going to do here is just change the car into a rectangle. In fact, I just saved myself some time. I'm going to copy this rectangle now, so I don't need to draw it all freshly again. Now, before we had a plane. The plane was in air, it didn't have a surface that it was on. Whereas here, we do have a surface. So I'm just going to draw on here a surface which this car is on. Okay, so this car's being pushed, and even though it's a rectangle, we can, for most intents and purposes, assume the forces are acting from the same point. Now, I know you might be thinking here that this car's being pushed from behind, and if so, that's fine. We can do the pushing force going this way. So this can be the push from the person, either a man or a woman. So this I'm going to call the pushing force. But again, because it's an object on planet Earth, it will have an associated weight. So I'm just going to do a downward arrow to indicate the weight. And as well, you might be thinking, well, if the only force acting in the vertical direction was weight, it's not balanced. So what we need to do would be to balance this out with a force from the ground, which pushes the car upwards to stop it falling from the ground, which obviously wouldn't happen. So the force from the wheels on the road will be equal and opposite as the force on the road acting on the wheels. So that's a law in itself, which I'll mention later, but what I'm going to add here, now it depends on the question. Sometimes you can get away with just doing it as just one force, combining these two together. What I'm going to do here is consider it as two different forces. One from this axle of wheels at the back, one line for the front axle of wheels at the front. And we're going to call each of these the normal reaction force. Normal means perpendicular to the surface. Doesn't mean normal in terms of the opposite of abnormal. It's just another word for perpendicular. And that's coming from the wheels acting upwards. And so the forces on the wheels will be equal and opposite to the weight of the car. And again, I think it's reasonable to assume that this is a horizontal road. So here, you might be thinking that's a good first attempt, and it's not so bad, but I'm just imagining here that the first attempt isn't quite complete. So what we need to do here is just look at the first and consider what are we missing in terms of the second attempt. So what I need to do here is just get what I've got here and move it all to this side. That looks fairly fine to me. However, there will be a force resisting the motion coming from this person pushing, and this force will be going in the opposite direction to the motion, which I'm going to just give as a slightly different arrow in a blue colour, and it's going to be the friction. there'll be a frictional force which will act against the line of motion. Friction will always act to resist motion, or will resist in the direction opposite to where the motion would go if a friction weren't there. So friction just holds things in place, and friction can exist even when there's no motion. So that would do for the car. Let's now have a look at a third example. So here, a dog on the lead. Now, if you've got a dog, I apologise. I'm not trying to say that a dog is no better than a rectangle, but for modelling purposes, we may as well just call the dog a rectangle. This is a good thing about mechanics. We can make assumptions which might seem quite blunt, and sometimes they are, but we just take assumptions and we refine the model again and again until something crude becomes something refined. So that's the first attempt. I'm just going to sketch out now the second attempt. Okay, so you should be able to guess right now what's acting down, pushing the dog down towards the centre of the Earth. It's going to be the dog's weight. So we can always add on the weight of the object going towards the centre of the planet. So that's the weight going downwards, and I'm going to just copy it across here for my second attempt. You might be thinking, well, what if I'm doing physics, sir, and I'm really good at doing force diagrams? Do I need to do a first and second attempt? No, you don't really. The second attempt is just there in case you make a mistake. So my first attempt is phony, really. I'm deliberately just not being complete on making some mistakes. So what's driving the dog forward? Well, it's going to be the drive from the dog's legs. Okay, so I'm going to just label this maybe drive from the legs. It's driving the dog forward, it's pushing forward against its lead. So again, I'm just going to add this onto the finalised attempt. And of course, because the dog is, as you can see, balanced horizontally, it's not floating up like a bird, it's not falling through the earth, it's going to have a force pulling it upwards, so it's balanced against its own weight. So again, what we can do is call this the normal reaction force. Oops, that's my mistake. So it's up arrow, I'm just going to label as normal reaction force. Now, if you're thinking now, do we need to label forces in words all the time? No, we don't. When we get into this chapter, you'll see that we can just label forces with letters. For example, normal reaction force is normally given the capital letter N to denote normal. Weight is just capital W normally, or we can use mg. So don't be thinking we need to label all diagrams in future like this. This activity is just to get you thinking about what the forces actually are. And of course, as you can see here, there's a lead attached to the dog, and that lead is pulling the dog backwards. Now, if it's an object like a rope or a lead or a string, which that isn't completely horizontal, that's my mistake, the force acting along a rope or lead or something, it acts consistently throughout the length of the string, lead or whatever, and it's called tension force. So there'll be a tension in this lead holding this straining dog back. However, if you look at this diagram here, you can actually see the owner, most owners are taller than their dogs. Okay, it might be different, it might be like a Great Dane and a toddler. That wouldn't be very wise. But here you can actually see the lead is going upwards because a person is stood here with their hands. So actually, this is slightly unrefined. What we should have here is a force going up like so. So I'm going to label that tension, but it's working at an angle to the horizontal. So actually this will limit the normal reaction on the dog's paws, pushing it up. So the normal reaction will be smaller than the weight, because the weight will be balanced by not just the normal reaction from the dog's paws, but also the tension. So we're making the dog feel like it weighs less by inadvertently propping it up with a tension force, which is acting at an upwards angle from the horizontal. Finally, car on a road. So again, you know the drill by now. Let's just draw a rectangle. That's a square. I know what you're thinking. I need a rectangle diagram or something to just do this quickly for me, but never mind. So we're going to do that, and it's acting on the road. So we've got this here. And then we'll have a second attempt. Over here, if I can actually get this to move. There we go. So, what's pushing this car forward? What's driving its motion? Well, this is going to be the thrust from the engine. Okay, so I'm going to call this thrust from the engine going forwards. Pulling the car downwards, keeping it on the road. That's going to be its weight. Okay, stopping the car from going through the floor is the reaction from the road on the wheels. So I'm just going to do 2 arrows going up here of equal and opposite sizes combined to the weight. So we can call these the normal reaction forces. So if the car is in perfect balance and the drivers aren't much heavier than the passengers at the back, then these normal reaction forces should be pretty much equal at the front and the back of the car. Now here, we could think there's going to be some friction on the road acting against the motion. So I'm going to do an arrow here pointing backwards because that's quite hard to see. I'm just going to colour this in a blue colour. So I can call that friction. So that seems pretty good to me. So good, in fact, that what I'm going to do, I'm going to copy all of this stuff here. And I'm going to just replace this second attempt with what I've just done in the first. And I can sort of maybe think that that's perfectly good and I don't need to do anything else. However, if you were thinking really carefully, what I'd suggest we might want to do is also include a force going back not connected to the road. Okay, this car will have an air resistance associated with its motion, and so I'm also going to label on a drag force like this. So you might think this is an awful lot of forces to be considering, and sometimes there will be. However, the good news for you is, often in exam questions, we can simplify even further. So for example, these two normal reaction forces, in some questions we could group into one. We just have one arrow going up called N, one arrow going down called W. The thrust going forward, that would be considered as well. But again, the drag and the friction, because they're acting in the same direction, for some questions and context, we can consider that lumped into one force, just called a constant resistive force, for example. So here, I just wanted you to brainstorm all possible forces, but just bear in mind sometimes we can model questions and situations as being even simpler from what we've done here. So it's not always as bad or as complicated as what it might sometimes appear. Let's have a look at a quick work example. So we've got a block of weight W is being pulled to the right by a force P across a rough horizontal plane. Rough doesn't mean it's a dog, it's rough with an R. It means there's going to be friction involved, essentially. So draw a force diagram to show all forces acting on the block. So this is going to be much easier having us attempted that warm-up exercise in pairs, drawing force diagrams. So all we need to do here is to draw a block. I'm going to make this into a more rectangular sort of shape if I can. Okay, so it's being pulled to the right by a force P. So first off, I'm just going to label this on. So I'm going to label this P. Okay, now it's a rough horizontal plane, so again, we can use information to help us. If it's a rough horizontal plane, then what we're going to be having here is a frictional force acting this way. I'll get that line a bit thicker, in fact. Oops, a bit too much. There we go. So I'm going to call that F for friction. In fact, what I could do is just call it friction. Now it's got a weight W, so again, there's going to be a force acting downwards, which I can call W. I'll just do that, so it's colour-coded. If I call that W, in a nice green colour, of course. And finally, we need to consider there will always be a force acting upwards if there's a surface, which I like to call the normal reaction force. So let's call this normal reaction force going upwards. And that's all there is to it. So, when the forces acting upon an object are balanced, the object is said to be in equilibrium. So an object could be moving and be in equilibrium as long as it's not accelerating. So, what's Newton's first law of motion? So, what Newton said, in words to this effect, are an object at rest will stay at rest, or an object moving with constant velocity will continue to move with constant velocity unless an unbalanced force acts on the object. So two forces that act in directions that are perpendicular to one another do not affect each other. Therefore, what we tend to do is resolve forces acting perpendicular to each other. So in this section, we'll just consider forces acting vertically and horizontally. For year 13, we'll consider forces acting in a particular sloped direction, but for now, year 12, just up and down and left and right. A resultant force acting on an object will cause the object to accelerate in exactly the same direction as that resultant force. That is a universal truth. So just one final example, before I leave it to you to try some yourselves. So we have this diagram here with forces acting on it. So draw a force diagram to show the resultant force. And so what we have here for part A is obviously just a spherical or circular object. So I'll just copy that out now. So resultant force, if we have a look horizontally, it's 20 to the left, but also 20 to the right. So the 20 to the left and the 20 to the right will cancel for working in equal and opposite directions, so the net force going left and right is 0. However, if you look at up and down, it's a force of 30 going up and 20 going down. So overall, because the upwards force is greater than the downwards force, the upwards force will prevail, it will win, essentially. So the overall force going up will be 30 newtons, take over 10 newtons working against it. So 30 minus 10, essentially there's a force going upwards of 20 newtons overall. So that's the overall resultant force on the object, 20 newtons going up. For part B, describe the motion of the particle. Because the resultant force is acting vertical upwards, the particle will accelerate vertically. We don't know its weight, so we can't say how the acceleration is in terms of magnitude, but the particle will accelerate vertically upwards, because the resultant force is vertically upwards. And that's all we need to do really for this question. So now it's over to you lot. So page 158, exercise 10A on the Stats and Mechanics book. Try questions 2, 3, 4 and 5, and go on to 7, 8, 9 and 10. By now you know what to do. Try the questions, check them each and every one as you go along. If they're wrong, try and see where you've gone wrong. If you're still not sure, ask a classmate. If you're still not sure, ask me either in class, on an email, or via the comment section on this video. Thank you very much for listening again. I hope you've enjoyed it and got something out of it. Try the questions and contact me if you're stuck. Take care, and as ever, I hope to see you all soon. So, bye for now, and take care.